Right, so the next talk is by Georg Oberdieck, and he'll tell us about Donaldson-Thomas theory of what looks like K3 cross an elliptic curve in higher divisibility.
Okay, yeah, thank you very much for giving me the opportunity to speak. So this is a project, on the topic which I worked on kind of what feels like 20 years ago, and someone just recently I came back to it and tried to still understand a few details of what I was missing back in the day. And so, yeah, so this is still work in progress, so please ask questions whenever you have them. And so I guess from the audience that everybody will be quite familiar with the physics side of this story of string theory, of this type 2a string theory of K3 times T2. And so, but somehow on the mathematical side, the development is somehow, and on the physics side, this was kind of well understood since like, I don't know, 30 years, some time, but on the mathematics side, somehow we're kind of slower. So just, we're only catching up now what kind of was kind of clear on the physics side already 20 years ago. Okay, so I tried to explain a little bit the mathematical side of this story and yeah, kind of go through this. And so first I will start with counting on K3 surfaces, in particular counting sheaves. So physical terms, probably D branes on this K3 surfaces, and then come to K3 cross elliptic curve, then state the new result, is, then the proof, and then also give an outlook on the higher rank case. So let me start with the definition. I mean, just to bring everybody on board. So a K3 surface is a complex algebraic surface, which is simply connected and so it has a holomorphic symplectic form. So in other words, it's a Calabi-Yau surface, which is not a torus. Okay, so examples are like quartics in P3, or you can take elliptic K3 surfaces, so elliptic surfaces which are Calabi-Yau, and then or double covers of P2 and so on. So there are many very beautiful examples. So this picture in the beginning is this example of this Kuma K3 surface. Okay, so be in torus modulo plus minus 1. And so then the most basic case, if you're interested in counting sheaves on these K3 surfaces, is to look at what is called Götzsch's formula. So you look at counting ideal sheaves of zero-dimensional subschemes on your surface. So for that, you look at this space S bracket n, which is yeah, I wrote it in some sort of funny way as a configuration space of length n point clusters. In mathematical terms, this is the model space of zero-dimensional subschemes of length n. So generically, this space parameterizes n unordered distinct points, and then when points come together, then like you have additional structure. You remember the scheme structure of that configuration. and so this turns out to be a smooth projective 2n dimensional variety, and then you can just take its Euler characteristic. So E of this variety is E stands for the topological Euler characteristic. So let's call this D of n, and then there's this really beautiful result of Götzsch, which tells you that if you take the generating series of these numbers, then you get this kind of product on the right. And so in some sense, the right-hand side looks very familiar to everybody who works with modular forms, because it's this modular form discriminant, but only up to a constant. So maybe to stress this point, let me make this kind of remark, which is kind of innocent at first view, but then kind of will lead us to the right definition, of the right thing later on for this K3 times elliptic. So if you, in some sense, from a modular forms perspective, it's really natural, instead of taking this generating d to the n, q to the n, it's more general to shift this variable q to the n by -1. Okay? And so on the right-hand side, this means just you divide by 1 over q, right? And then you look up, take out the textbook on modular forms, and then you see that this is exactly this discriminant, 1 over the discriminant function of tau. So this weight 12 modular of Caspar. And so from a geometric perspective, you can ask, why do you do this? So why do you have to shift by this -1? Where is it coming from geometrically? And so let me just explain you this. And for that, I have to introduce this K3 lattice, which will also play a role later. Okay, so this explanation, where's the shift coming from? And so this comes from what is called this Mukai lattice. Okay, so this lattice is just the ordinary lattice of this of this K3 surface, of the cohomology of the K3 surface, that just has even cohomology, has H0, H2, and H4. But then instead of just taking the standard cup product on this K3 surface, we take the cup product which matches this the Euler pairing. So this is defined by so if you represent a cohomology class by these three vectors according to this decomposition pair, then you define it by taking just the regular intersection product of the divisors, and then the point class and the unit class pair with the -1. And so this has kind of the nice fact that so that if you take a sheaf and you take what is called its Mukai vector, so it's Chern character times the square of the Todt class, then the pairing in this lattice precisely gives you the holomorphic Euler characteristic between the two sheaves you consider, up to the sign -1. So if you're not interested in this kind of, then just remember as a lattice, it's just this K3 lattice that we have. And so once you observe that, then you can see the following. So if you now view this S bracket n, not just you view it as a model space of stable sheaves on this K3 surface. So particularly, I mean, a model space of ideal sheaves. Then you can calculate this Mukai vector of an ideal sheaf of length n. And then you see that this is 1, 0, 1 minus n. And then if you take it square, and so this is kind of a confusing exercise, but if you take v square half, right? So you take this v square half, you get like minus, so we take a minus, so it's like -2 times 1 minus n half, right? So you get exactly n minus 1. So it's kind of perfectly matching this. So as I said, this kind of an innocent calculation, but this kind of leads you also to the general case. So if you have this following theorem, that if you look at more generally arbitrary model space of H stable sheaves on this K3 surface S, where you take a primitive Mukai vector, so V is a primitive vector in this lattice, and you assume also your polarization is generic. That's a detail. Then again, you get a smooth projective model space, and the Euler characteristic is again given by this corresponding coefficient of this one over this function. And so the proof is kind of reduces to this basic fact that somehow on a K3 surface is all two model spaces of stable sheaves of the same dimension are just deformation equivalent. Okay, so the Euler characteristic is the same. Okay, so that's the result of fusion. So just to give a very basic example. So for example, if you take this Mukai vector 0, beta, 1, where beta is a curve class, then you can take this Euler characteristic. So there's also this this genus 0 Kupaguma-Waffer invariance as defined by Sheldon cuts. And so then this evaluation we have up there here is exactly this count of rational curves in a linear system defined by this curve class. So this is also called this Jausaslow formula. Okay, so this is kind of a classical story in this business. Are there any questions about this? Okay, so I want to continue, and maybe the next case to look at is imprimitive Mukai vectors. Okay, so they will come up also later in this K3 times elliptic curve story if you consider like this wall crossing contribution. So let me maybe mention them quickly. Okay, so here the natural place to look at them is to look at this local K3 surface. You look at K3 surface times C, and then you look at this model stack of H-Giesiger semi-stable sheaves on this threefold, which are supported on the fiber of this map from X to C. Okay, so kind of they're fiber-wise on this supported on this K3 surface, and then you fix this Mukai vector, meaning you kind of sum over all the Mukai vectors of the various sheaves in the support. And so then you can again ask for what is this kind of space, and because V is imprimitive, kind of the thing becomes kind of quite a delicate technical matter, and the reason is that this MH of V can have, I mean, it's really on a stack, so it can have complicated stabilizer groups and so on and so on. So mathematically, is kind of a challenge, and this has been solved in particular by this work of Joyce on this theory of indecomposables. And so the idea is somehow to take this. I mean, I don't want to go into it too much, but you take this motivic Hall algebra, certain algebra, and you take the generating series of the classes of the stacks in this this Hall algebra, you take the log and then you extract a certain, again, extract this coefficient corresponding to the V. Okay? So once you're there, then you can just take the Euler. And so some of V is primitive, you reduce to the old case, but then if V is imprimitive, you really get a new result and you get a new counting formula. And this was first conjectured by Toda and then recently proven by Maulik and Thomas. And so, yeah, so this is some sort of multiple cover formula for this counts of sheaves in imprimitive Mukai vector. So the way you should probably read it is that, so on the right-hand side, you see this D. So this is really the count, I mean, this Euler characteristic of this Hilbert scheme. So it's really a count of in a primitive Mukai vector. And so in some sense, you should read this as saying that the counts in the primitive Mukai vector determine you also the count in the imprimitive case. Okay, so I want to go to K3 cross elliptic curve and there to Donaldson-Thomas. So, but in some sense, it's more natural to still stay on the K3 surface side and look at what is called stable pair invariance or Pandey-Thomas invariance. And so let me just give you the definition for everybody who's interested. So a stable pair on a smooth projective variety is a pair of a sheaf together with a section. So F here, this F here is a pure sheaf F on this X, which is supported in dimension 1. So the thing you should think about is somehow it's like a smooth curve in your X, and you take a line bundle on this curve and you push it forward to this X. So together you also have the section with 0-dimensional curve co-coordinate. So in some sense, this model space Pn x beta parameterizes you the data of a curve, a line bundle, and a curve and some points on this curve. And then there's two data we keep track of here. This is this data of the class of the support of our sheaf. So this is curve plus beta. And then also the Euler characteristic. So this is what we call N. And so if you take now your K3 surface and you take this class beta that we are looking at to be irreducible, so irreducible curve class of a given square 2h minus 2, then there's this very beautiful formula by Kawai and Yoshioka, which tell you what is this. So this model spaces in this case will be again smooth, and then this formula by Kawai and Yoshioka tell you the generating series of the Euler characteristic of this module spaces. And so then you see this kind of nice product expansion on the right-hand side that probably a lot of people here will identify quickly as like 1 over this Jacobi form of weight minus 2 in index 1. So it's kind of a modular object again on the right. But in some sense, this you should in some sense really view as a count on sheaves on the threefold surface times C, or surface times elliptic curve. So let me go to the next case, the surface. So now let's come to the real case, so the K3 surface times elliptic curve. So maybe I wait a second for any questions. So okay, so somehow after this review, let's go to this the threefold Calabi threefold case. And so here we look at surface times elliptic curve. So E is an elliptic curve, or T2 if you like that better. And so again, in some sense, for the stable pair invariance that we're considering, there's again this data of this N, the holomorphic Euler characteristic that we have to specify, and then this class, the curve class. And so here the curve class is on this threefold split as this. I mean, there's a degree over the K3 surface, and then there's Z times this class of this elliptic. And on this threefold, there's really a new feature here, which is this elliptic curve. So this elliptic curve acts on the module space. So elliptic curve acts on this threefold just by translation. And so in particular, it also acts on this module space of stable pairs. And you can convince yourself somehow if your stable pair is invariant, then in some sense it has to be pulled back from this K3 surface. And so in some sense, unless really in extreme cases, this can never happen. And so then this translation has finite stabilizers. And so in some sense, yeah, this creates a problem because then if you have a stable pair, I mean, if you can translate it, and so instead of just a stable pair, you get a whole E orbit of this stable pair. And so if you just take the Euler characteristic of an elliptic curve is 0. So so the Euler characteristic in most cases is 0 for space. Okay, so we cannot just take the invariant, so we have to do a little bit here. And the solution is really to divide out this elliptic curve from the model space, take the quotient in a stack sense, let's take the stack quotient, and then take the topological Euler characteristic of the stack quotient. And so this is there a question? And so later we will see that this kind of, I mean, for usual color-bearer threefold, for example, the quinti-color-bearer threefold, you don't have to do this move. So this move is somehow quotienting up or something is not what you want to do. So here you do it, and this is why you kind of get a different theory. So this is kind of responsible for why we would call this kind of a quarter BPS diane. Okay, so this is kind of this action here dividing is kind of reflected by this fact that this threefold has like this extra symmetry, extra supersymmetry. And so now let me come to this, what we can say about this invariance. So this PTN beta D. So, and so really the key figure is here, this Igusa cusp form. So, so for the K3 surface alone, really the key player was this discriminant function delta of tau, which is somehow the cusp form of the lowest weight. And here, similarly, you look at the cusp form, but for modular forms of genus 2. So you look at the Siegel upper half space, you look at the standard coordinate, and then there's this unique Siegel modular cusp form of weight 10. In fact, the minimum weight is this beautiful Igusa cusp form. And so I will not give a formula, but you can imagine it as nice as this discriminant function. So, and so, yeah, so it has a product expansion, it vanishes at a very particular loci and so on. And so then once you have this function, you can take 1 over chi10. So in some sense, it's very parallel to the earlier case, and you take a Fourier coefficient. Now you have 3 parameters, so you have to take 3 variables here, QH, Q tilde to the D, P to the D. And so then you extract the Fourier coefficient. And so then there's still the epsilon to think about here, because and for the discriminant function in genus 1, it didn't matter where you take the Fourier coefficient. The only pole somehow, if you take 1 over the discriminant function, is at infinity. But here, 1 over chi10 has a kind of a bunch of zeros. Chi10 has a bunch of zeros, so 1 over chi10 has a bunch of poles. So in some sense, it matters where you take this Fourier coefficient, right? So, and so here we pick a very specific kind of choice where choice of expansion point of this Fourier expansion. So we'll come back to that later. So this is kind of an important story on the physics side, and will also play a role in the mathematics. And so then the basic conjecture that, I mean, of course, was inspired by a lot of earlier work in physics, is that this Donaldson-Thomas invariance in this threefold is given by exactly this expression where this coefficients that enter are the C's. Okay, so remember that the C's are the Fourier coefficients of this 1 over chi10. Okay, and so this kind of a complicated statement. So let me better just state this in kind of 2 steps. So the first step is, so let's break this somehow in 2 statements, this conjecture. So the first statement is that let's first take this beta class to be primitive. Okay, so let's take this to be a primitive curve class. Then, and you fix the square, then this statement above here just reduces, and so this k would be 1. So the statement above here just reduces to the fact that this Donaldson-Thomas invariance is up to a given sign, just exactly this coefficient of this Fourier coefficient of this 1 over chi10. So, so in some sense, in the primitive case, for primitive curve class, you get exactly 1 over chi10. And then in the imprimitive case, basically the formula above is a multiple cover formula. So it somehow says that, again, you reduce the imprimitive case is determined by the primitive case by a very concrete form. And so this gives you kind of a complete prediction for this geometry, for this Thomas invariance. And so let me just quickly say what is known about this. So if you're in d equals to 0, then this formula, so in d equals to 0, d is the degree over the elliptic curve. So in d equals to 0, you're completely on the K3 surface. And then this, I think in the mathematical literature, this is then called this Katz-Brem-Waffer formula. And this then has been solved recently in 2016 by Donaldson-Thomas. And so the proof is basically in 2 steps. So the first step is this part A, which I mentioned before, is kind of the primitive case where beta is primitive. So this case, and essentially this one follows directly from this Cavallo-Shioka formula if you can prove that your Thomas invariants are deformation invariants. And so this was some earlier work by Maulik and again the same 2 authors. And then really the new key feature in this work 2016 is that they can establish this part B, so this multiple cover formula. And so this part B is somehow also what will play, kind of the same strategy kind of will also play a role in our case. And so then if you look at the general case, what can you say? So this part A holds by the earlier work that I mentioned, so this together with Aaron Pixton and Junyan Sheng from a few years ago. And then this kind of solves the primitive case in full generality. And then this part B was recently established on a Gromophin site in divisibility 2. So they prove a sort of multiple cover formula for the Gromophin theory of K3 surfaces. Okay, so the result here, and it's still to be written up, but I'm confident. So that this conjecture that I stated before, this evaluation holds in fact in all cases. So that in fact this also this part B that I had before. So part A was already known, so that so I can establish this part B. Are there any questions about this? I don't know how much time I have.
You have until 8:15.
Okay, so 25 minutes. Okay, I don't know if I need so much. Okay, so let me say a few words about the proof. So how do you go about this proof? And somehow the idea is really to adapt the strategy of Panda and Thomas for part B. So their argument gives you this case where all your curves somehow supported on fibers, but now in my case, I also have this horizontal curve. And so in the Panda-Thomas case, the idea is to, you look for example, you can look just at surface times C, the surface times like A1 or complex number, surface times C. Then you localize on the C factor. And then you observe that after localization, what you get is some sort of nested Hilbert scheme. And you observe that in this, so then you identify somehow the perfect obstruction theory, the fixed perfect obstruction theory, you apply the localization formula, and you observe that after localization, you get a second co-section in almost all the cases that of the fixed component. And so this has as a consequence that somehow only a certain kind of very particular kind of fixed loci can contribute to this case in this K3 times C. So this is the same idea here. So let me sketch this quickly. So the idea is to take your elliptic curve and degenerate it to a P1. So then you degenerate to this relative geometry, surface times P1 relative to 2 fibers. Then you can do a little bit another standard argument to reduce to this cap, surface times P1 relative to S0. And then you localize there. And then essentially, because you're kind of using this reduced class, you counting this quarter BPS states, this helps really a lot because somehow already in this first localization step, you see that this reduced class rules out essentially everything except this extremal component. And so then this extremal component you can identify as a nested Hilbert scheme. And then using ideas of Golan, Sheshmani, and Yao, and then also further work of Golampo and Thomas, you can also identify the fixed part and the moving part of the associated perfect obstruction fields. And so then really the key step here is that, so you have some nested Hilbert schemes, so a bunch of, so on this K3 surface, so this is like a bunch of ideal sheaves on this K3 surface, one contained in the other, and then, and at some point this kind of this filtration stabilizes, and somehow we call it step non-trivial if the two sheaves differ from each other in a given step of the filtration. And so some of the observation is that if there's a non-trivial co-section, then if there's a non-trivial step in the filtration, then you can observe that there's for every such non-trivial step, there's an extra non-trivial co-section on this of the usual standard obstruction. And so somehow this reduced virtual class that comes up in this business accounts for one of these co-sections. So you can, so that means you can only have one non-trivial step in this filtration, and that is somehow the geometric origin of this multiple carbon. And so finally, you use some result of Ellingson, Götze, and Lehn for the universality of this tautological integrals on the Hilbert scheme of points. Okay, so this was kind of the proof, and I went over it quickly because I thought it's also, I mean, either you kind of know a lot of things or it's too, I will not be able to explain it. So yeah, if there are any questions, please let me know. Okay, so then for the last part, I want to go to the higher rank case and also kind of really match the exact prediction that was what was made on the physics side. And this is kind of, as I said, really old story and really beautiful story, I think. And so I wrote here, so since the 1990s, a clear picture has emerged in the string theory for this count of half and quarter BPS lines in this type 2A string theory in K3 cos B2. Okay. And so probably it started earlier. I'm really not the expert in this. And so here I just mentioned a few references. They are not ordered in any way, neither by time nor any importance. I'm just putting here some of them. And yeah, I guess everybody is way more familiar than I am on this topic. And so there has been a lot of work by many people on it. And somehow through all of this work, somehow there's a very clear picture on the physics side what happens. Okay, so let me try to see how this calculation I mentioned before can match this picture. And so let me just give a very quick review of the physics picture. So idea on the physics side is that there's this electric magnetic charge lattice. So there's this lambda E is the electric charge lattice, then lambda M is the magnetic charge lattice, so they are equal. And then you have this, and as a lattice, this is given by this K3 lattice that we had before, plus 2 copies of this U. Okay. So the K3 lattice, I understand. There's 2 copies of the U I don't understand. But anyway, so this is physics says. And so then one considers this kind of this fixed charge, this fixed electric magnetic charge QP in this sum. And we can also make this simplifying assumption that it is of unit torsion. So the GCD of this wedge is 2s1. And so then this result I mentioned before essentially says that this degeneracy of quarter BPS lines for this charge is just given as this Fourier coefficient of this 1 over chi10, where you take the coefficient determined by the squares of this, the intersection numbers of this charge. So take the q square half and the p squared half for the diagonal coefficients, and then q times p for the anti-diagonal. And so then, and everything is corrected by the sign. So the sign is kind of, should remind you of the sign early. And so then there's also a further prediction by physics that, of course, as I mentioned before, the right-hand side depends somehow on this, on where you expand or where you take this Fourier coefficient. So to make that clear, let's really rewrite this as a contour integral here on the right-hand side. So the way how you pick out the Fourier coefficient is by integrating this, your function against e to the minus 2 pi I, the index times the variable. So index of the Fourier coefficient you want to calculate times the variable. So here is this q square half times tau corresponds to taking this Fourier coefficient of q to the n. This q to the q square half. This corresponds to this. And so here the contour really depends, and then there's this prediction that that also the left-hand side, this degeneracy depends on this on a certain sigma. So this is this modular field, and then yeah, various authors. Yeah, so let me just Cheng and Verlinde. Sorry, so Cheng and Verlinde, and also I think this paper by Sen. They really give you a precise function to identify which contour you have to pick when you are given this. So I don't review this function here, but there's a precise analog, and then somehow this wall crossing of the Fourier coefficient on the right hand side that you see matches the wall crossing on the left hand side of this degeneracy. And so when I learned about this, it was somehow clear that this has to, if this quarter BPS line should count some sort of sheaves on this K3 times elliptic curve, then this wall crossing behavior that is observed here should come from wall crossing in the of the stability so the wall crossing of the DT invariance under change of stability condition on the mathematics. So let me try to explain this. So what's the mathematical picture of the story I explained here? So first of all, what should be the analog of this? So I have to tell you all of these analogs of the story. So what is the electromagnetic charge letter? So what's the mathematical analog of that? And so I think the most natural thing to do is just to look at the even cohomology of this K3. So K3 surface times elliptic curve. You take the even cohomology, and then you can naturally decompose it into two kinds of classes. The one type of classes are the vertical classes. So they live on a so are given by a class from a K3 surface times the class of a point on the elliptic curve, so this omega e, and then plus another, and then a second summing, which is just a pullback of classes coming from the K3 surface. So this is naturally a direct sum of this cohomologies of this K3 surface. So we just write it as lambda plus lambda. And so on the physics side, you still had this u squared, but here it doesn't show up, and I don't know how to make sense of it. We'll just have a lambda. And so once you're here, you can also define count, Donaldson-Thomas count here. And in some sense, we already know how to do this. So, so if you're given a primitive vector here, and you take a generic ample class here, you can look at the model space of H-stable sheaves on this threefold with this given Mukai vector specified by this V, W. And so then, as before, we divide out by this elliptic curve and take the Euler characteristic weighted by the Barron function. And so then the conjecture, and this is, still conjecture, but working on it, I think I'm kind of optimistic that this will work out. So this is work in progress. And kind of the simplest version to state this is that if you make this again, the simplifying assumption that the GCD of these two vectors is 1, then this Donaldson-Thomas invariance for this given charge is exactly the form predicted by physics. So you take a contour integral over a certain contour, and the function integral is again 1 over the Guder-Cast form, and then you pick out the Fourier coefficients specified by the intersection numbers of the charges of your Mukai. And so there's a specific contour that you pick for every given h, and I could write it down, but maybe it's not, I haven't done it. So for time reason, I haven't done it. So anyway, so in some sense, this gives you a complete prediction for what should be the Donaldson-Thomas invariance for this threefold, at least for this VW primitive. Okay, so let me just make a few remarks towards the end. So the first one is that I discussed this GCD V wedge W equal to 1 case, so this unit torsion case. The case of torsion positive works similarly, so this requires this multiple Gaussian formula that I stated before. And then, as I mentioned, there's this key feature that the wall crossing on the left-hand side, you can show matches exactly the wall crossing on the Fourier coefficient on the right-hand side. And so mathematically, this is realized by working with what is called this E times E hat equivalent Hall algebra. So there's a certain structure where you instead, together with the sheaf, you also keep track of together with the stack, you also keep track of the E times E hat action on this stack. So this was developed together with Pierre Rantner and Toda. And so this E times E hat equivalent Hall algebra really explains kind of this kind of that you have this quarter BPS states and this half BPS states. So the quarter BPS states come from sheaves which have finite stabilizer under this action of E times E hat, and then this what is called this half BPS states come from sheaves which have a one-dimensional stabilizer under this action. So this half BPS lines really correspond to this Maulik-Thomas-Toda counts that we had before, and yeah, in some sense, this wall crossing formula in this E times E hat equivalent Hall algebra really then states somehow that this half BPS lines can two half BPS lines then can form or contribute, or how do you, whatever one calls that, to a quarter BPS line count. And maybe a final comment here, what's really essential is this use of Bursztyn's theory of stability condition. Okay, so there's some, these have been constructed for this basis by Eugene Leo. Okay, so finally, maybe, I don't know what is the time. So let me consider the rank one case quickly. So how does it match this theorem that I had before? So I stated this theorem here. How does this prediction match before? So this is the rank one case. So in the rank one case, you can look at the space of stable pairs. So you can look at this Hilbert scheme. It's the same. And so I mean, the counts that you get are the same. And so let's look at the Hilbert scheme of n points of curve class beta comma d in this threefold surface times elliptic curve. And let's rewrite this in our notation of VW. Okay, so VW is the smallest space of stable sheaves we had before. So what I'm trying to do here in the last page is just identifying this, telling you the dictionary between these two sides here. So on the left-hand side, you are looking at the ideal sheaf of a curve in this threefold, where the curve class is given by this beta plus d times the elliptic curve, and then the holomorphic Euler characteristic is n. Okay, and so if you think about this, what this means for the Chern character, this means that you're rank one, so you have a one there. You don't have a divisor class, and then you have to subtract the Chern character of the structure sheaf of the curve. So you subtract this curve class, you subtract this holomorphic Euler characteristic times the class of a point. And so now you can calculate the Mukai vector. So you rewrite this. So so 1 and minus d times the elliptic curve go to one side and get twisted by this Todd class, and then the other stuff goes to the other side. And so in the end, you find these two vectors v and w here. Okay, so it's just a small calculation. And then finally, you observe that this GCD condition we had before just means that the GCD condition of this beta and n is just 1. And then the squares intersection numbers really corresponds to the indices that I inserted before in this user class. And so you see that this prediction before is a perfect match with this stable pair computation. And so yeah, so it's kind of, for me, it's extremely satisfying because somehow it extremely well matches what the physics says, and it just comes out very naturally from a mathematical side. So, yeah. So it's, from my perspective, it's really amazing that this was predicted like 20 years ago. Okay, thank you very much. This was all I want to say.
Thanks. Does anyone have any questions?
Yes, I have a question.
Mm-hmm. Yeah, go ahead.
So great talk, Georg. Can you see any promise for saying something about the CHL case?
Yeah, Yeah, so I think this multiple formula in the CHA case, you can also prove along the same line. So, so the same argument works there. And the other cases, I mean, so you mean for both parts somehow, for the theorem and for the, yeah, so the theorem, I mean, yeah, so for the CHA case, the, yeah, I would, I mean, I don't have a proof yet, but I would say it's in reach to have exactly the same theorem also in the CHA case. And then for the other case here, identifying all this stuff here, this electromagnetic charge lattice, then you have to take into account this action of G on the on this thing, and then I think you can make the same story, but of course then it becomes a little bit painful to match all of these things. But yeah, I expect that the same story will just go through also in the CHA case, but we require somehow more care somehow with the details. But of course, then proving it is, and yeah. But yeah, so yeah, so after doing this K3 times T elliptic curve case, then the CHA case is the next, really the next candidate. But yeah, at this point, I don't see really a strong obstruction.
Okay, thanks. Are there any other questions?
You can ask about the motivic K3 times elliptic curve, Sheldon, but I have nothing to say about this.
I controlled myself, but you're welcome to say anything anyway.
No, I have no idea about it.
All right, if there are no other questions, let's thank Georg again.
Thanks for having me. Yeah, and I'm sorry if I went too fast.
It's all right. Thanks. And that was the last talk for today. See you all tomorrow.